And thank you for joining us. I'm Brenda Dettinger from BIOPAC, and I will be your moderator on today's webinar, Mastering Electrodermal Activity from Setup to Analysis. Today's webinar is being recorded, and we'll send each of you a link once that recording is processed. During the webinar, if you have questions, you can go ahead and submit them through the GoToWebinar control panel. That's how you communicate with me, your moderator. We won't have a lot of time for questions today, but if we are able to squeeze one or two in at the end, we will. And if not, then we'll provide a Q&A at the end. Now on to our presenters. I'm excited to introduce our experts today. We have Alex Demuff. He is a product expert and head of sales for Europe. He has taught over 125 workshops on the topic of physiological data acquisition and analysis. He's been with BIOPAC for over 20 years. While at UC Santa Barbara, he was an instructor for the Advanced Training Institute for Virtual Reality and Social Psychology. Welcome, Alex.
Thanks. Welcome, everyone.
And we also have Fraser Finlay. He is the CEO of BIOPAC. He has over 25 years of experience in the life sciences and physiology monitoring industry. He's a well-regarded expert who presents at workshops all over the world. Welcome, Fraser.
Thanks, Brenda. Welcome, everyone.
All right, Fraser, let's start with you. I'm making you presenter.
Okay. All right, well, thanks for the introduction, Brenda. Welcome, everyone, to this webinar on EDA. Before we start, I have a little bit of background information about BIOPAC. BIOPAC Systems, Inc. is a global leader in life science research solutions, empowering scientists to measure physiology anytime, anywhere, and from any subject. BIOPAC has been advancing research for over 30 years with its cutting-edge tools and software trusted by 99 of the top 100 universities worldwide. With more than 56,000 scientific citations, BIOPAC's technology is relied upon by leading tech companies for product development, validation, and human-centered design. So I figured I would start by showing you what we're going to be talking about today. So this is actually live data coming from this ring that I'm wearing right now, and just for some authenticity, there we go. Just to prove that it is live. Yeah, so this is the skin conductance level data being displayed within AcqKnowledge software. For those of you that are unfamiliar with AcqKnowledge, you know, it's extremely flexible, both in terms of the graphical user interface, but also in terms of the tools and the analysis capabilities within the software. So here on the right, you've got your vertical scale. This is pre-scaled when you set the ring up. So microsiemens, and then time along the bottom, right mouse click, you can auto scale, or you can manually make adjustments to your scaling here. So we can compress this down. In terms of the time axes on the bottom, we can make this 1 minute per division so that you see a longer period of time. Anyway, that gives you a quick example of AcqKnowledge in the ring. Let's talk a little bit about the hardware options that you have available with BIOPAC. And these fall into pretty broad categories in terms of wired, wireless, and then we also offer an amplifier for MRI as well. And I'll just walk through some of those options. The MP200 is BIOPAC's core research platform. It took over from the MP160, and prior to that, the MP150. There are two amplifier types for this, the wired and wireless. In terms of the wired, This is the latest generation. This is the EDA 100D. These are really nice. They're very small, lightweight. This will clip to the participant. We use the lightweight electrode leads, which are common to both the D series and the Bionomatics amplifier range. So this is the latest generation, single channel. The nice thing about these D series amplifiers, when you plug them into the AMI module, which comes with the MP200, the software will immediately identify the amplifier type and set everything up for you. Many of you will have the previous generation, the C series. This has been around for a long time. There are a couple of things to pay attention to with the C series amplifiers, and I've highlighted a couple of them over here. Down the bottom, there are two amplifier settings for the, actually use my little tool here. Here we go. There are two settings here, high pass filters. It's important that these are set to the DC position. This will allow you to accurately record the tonic waveform, the skin conductance level. And then here you set your gain, and pretty much any of these gain positions will work, but we typically recommend the 5 microsiemens per volt position. When you go into the software will guide you through this a little bit. And then on top, which isn't shown on this picture, there is the channel setting, and those are the sort of the key things that you need to pay attention to. If you're running other biopotential signals, maybe facial EMG or ECG, the EDA, the participant is grounded through the EDA amplifier. If you are interested in running more than one ground, we do have this interface cable, the CBL205, that enables you to run a second ground on one of the other biopotential amplifiers. And you connect the CBL205 to the ground position on the front of the amplifier, and then a lead 110 ground lead will connect to the interface. Now, this becomes important if you're only recording EDA for a period and you want to remove the electrodes just to make it a little bit easier for the participant. That would mean that you no longer have a ground on the participant. So then having a second ground will overcome that. So this is kind of an optional thing. Okay, for those of you that have the Bionomatics or want a little bit more flexibility for your participants, we have the Bionomatics range of receiver and transmitter pairs. So on the left, this is the pair. The transmitter is the small box down in the bottom right over here. This is the receiver. The receiver connects to an MP150, MP160, or the MP200. The participant wears the transmitter. This is set up for EDA. You basically have 10 meters line of sight. So for an in-lab setting, it's usually more than adequate. And it just gives your participant a little bit more freedom to move around. If you require a greater degree of portability, we've got the Smart Center over here. And if your participants need to be away from the lab, remote, we have the Bionomatics Logger. Both of these devices connect to up to 3 transmitter modules. The Logger actually has an accelerometer built into it as well, a voice journal, and some other nice features. So for those of you that want your participants remote, away from that lab, collecting data for long periods of time, this is a pretty good option. If you're traveling to your participant's home or place of work, this is very convenient. It's small, it fits into a small little carry case, connects to a laptop via USB, super convenient. We also have the MP36R. This is a 4-channel device the nice thing about this, when you launch the AcqKnowledge software, you basically tell the software what signal you want to record on which channel, and the software will set up the amplifier for you. And for all of these instances that I've shown, we offer both reusable electrodes or disposable. However, we recommend using the disposable electrodes. And the main reason for recommending the disposables is that you get greater consistency across all your participants because you're using a new electrode every time. Okay, finally, we have the MRI applications, and the MRI environment is divided into two portions. There's the control room, which is where the recording equipment resides, and then you have the chamber side with the MRI, and this is where your electrodes and electrode leads are located. BIOPAC offers a filtered cable set, MEC MRI trans. This is broken into three pieces. The first portion is a 2-meter cable that runs from the amplifier to the patch panel. The cable comes with a filter. The filter must be securely mounted onto the patch panel, and that allows the connector from the amplifier cable to connect in the control room side. On the other side of the patch panel, the mating part of that connector, we run an 8-meter cable, which is the patient cable, and then our electrode leads connect into that. And for that, we recommend the lead 108Bs. These are carbon fiber electrode leads. They're relatively short, and then we have carbon fiber electrodes for making contact to the participant. Finally, in terms of hardware for electrodermal activity, we have the ring, which is what I started with. This is very elegant. You've got a number of signals that can be collected. I was only showing one of them, but it also comes with pulse, temperature. You've got an IMU, so you get accelerometry data as well, and ECG. And then the ring can connect directly to AcqKnowledge. So if you're in lab, you can be collecting data just as I demonstrated earlier. But for those of you that want your participants out in the real world, the ring will connect to an iOS app. The data is saved on the phone or pushed to a cloud. I figured that because we're talking about EDA, I'd bring this up. BIOPAC does have a really nice guide, introductory guide. There's a QR code down here, or you can go to the website, biopac.com/guides, and you'll see a number of guides that we have available. This is kind of a handy tool, for particularly for those of you that are new to recording electrodermal activity data. Okay, so in terms of the subject setup, it's actually pretty straightforward, and I've got some electrodes here. These are the disposal electrodes, two types, either the EL507A or the EL509. You'll notice that we regard these as dry electrodes. In the purest sense of the word, they're not dry because you do have to add electrode gel. When you peel them off the tray, the little sponge in there does not contain gel. So you just have to add a small pea-sized amount of gel. And it's important that you use the gel 101. So it comes in a little tube. And then all you're going to do is just place, I'm just going to give you an example here. Just a small amount, about a pea-sized amount of gel, and then you can place that on your location of choice. Okay. the nice thing about these electrodes being sort of dry disposable is they never dry up. So, you know, if you're unfortunate and you leave the packet of electrodes open, because there's no dry gel on the sponge, they'll never dry up. This is a common question we get relating to electrode placement. Typically, the fingers are used or the palms, but there are a lot of other locations that can be used. So the important thing is to think about what your participant will be doing during the experiment, the tasks, and then picking a placement that is going to allow them to perform any task, maybe using a joystick or a mouse or keyboard, and finding a location that's going to give you the cleanest signals. I put a few tips down here. We also have an FAQ on the website as well. QR code will take you to that. But essentially, wash the hands. You don't need soap, just plain water, dry them off, make sure they're thoroughly dry. Make sure your room environment, the temperature is not too hot, not too cold. You kind of need the Goldilocks approach. Determine the best hand to use if you're using hands or another location. Apply a pea-sized amount of gel to the electrode, the sponge of the electrode, and then apply the electrodes, making sure that they are fully secure and they're not going to come off. We also recommend taping the electrode leads down as well, because that way you avoid electrode leads banging around, because that can induce artifact. And then before you actually start to collect data, you want to wait approximately 5 minutes before the recording commences. Okay, so that gives you some quick ideas for hardware and participants setup. I'm going to hand you back over to Brenda for our first poll of the day.
All right, great. Thanks, Fraser, and thanks for sharing that guide. I'm going to go ahead and launch the poll. And yep, it's launched. Okay, so we're interested in just learning how you perform your experiments and, you know, how that works for you with needing subjects to have their hands available or not. And just as a reminder to people who are arriving late, who missed my intro, we are recording this, so you can go back and listen to parts that you missed if you joined late, or just rewatch it in general. A lot of great information in this webinar. And also, we won't have a ton of time for questions today, but we will take questions and provide a document, a question and answer document in the next week or so. Okay, I'll go ahead and end the poll, and I can share the results real quick if you guys want to take a look. Looks like other performance tasks and a lot of people not using both hands. So interesting, virtual reality is pretty up there as well. So I'll go ahead and close the poll, and we're gonna switch gears and head over to Alex. Alex, I'm gonna go ahead and make you presenter here. There you go.
All right. Thank you, Brenda. I think it works now. Perfect. Okay, so now let's go on to the next part, which is setting up the software. And I'll actually jump directly into AcqKnowledge. This is the splash screen that you get at the very beginning. And I have my MP200 connected right here. So click OK. And I've connected the smart amplifier, the EDA 100D smart amplifier. The software automatically recognizes where it is, channel 1. And really all I have to do is, if I want to, I can place a label. So I can say, all right, this is the EDA. It will automatically place a label anyway. So I don't have to do that, but I will. And then unlike the C-series amplifier, the smart amplifiers always record from DC up. So there is no high pass filter applied. So we don't have to worry about that. And if we leave it like this, we'll record data between DC and 3 Hertz. That's where a lot of the useful information is anyway. You have the option to open them up to wideband, and then you record all the way to 10 Hertz. For the sample rate, you actually don't need anything above 50 Hertz, but we recommend sticking to the 2000 Hertz sample rate that's default in AcqKnowledge. It's just easier that way. A lot of signals require that sample rate, like EMG, electrocardiogram. It's good to record at 2000 Hertz. So just stick to the same sample rate and down sample afterwards. That's really all we have to do. And at this point, I can even save whatever I've done as a graph template right from within here. I can save it as a graph template, and then I can reuse my settings next time around. I can also do the same thing over here, save as, and choose graph template and save my settings. For now, I'll just start recording. And this is probably the most important part when you're getting started with EDA. Ask the participant to take a deep breath. First of all, I'll adjust the scaling here to be adaptive. The way I did that is I clicked here and chose adaptive scaling on the vertical scale. And I'll take a deep breath now. And then I let go. So this gives me a skin conductance response, pretty big one. That's what you're supposed to see with your participants. I recommend something like 5 seconds or 10 seconds per division for the horizontal scaling, because skin conductance is a fairly slow signal that will give you a nice bird's eye view of several responses at the same time. Now, what happens if you don't get any of that? So you ask the person to take a deep breath, but there's no response. There's a couple of options here. They could be a non-responder, meaning that actually, no matter what you do, they'll have a signal that remains very, very low and flat. And then that's about 10% of the population, actually, so it's considerable. And then you have also the option that maybe you didn't put enough gel, or simply the electrodes are not placed properly. So you can go back and maybe do a test on yourself, and again, hook up the participant, and then it should work fine unless they're a non-responder. Now, let's come back here to presentation. So that's the very easy setup with the smart amplifiers, nothing you have to worry about. And then pretty much every experiment has some sort of events associated with what's happening. Okay, so and you can manually enter events while the acquisition is taking place. That's one solution. Maybe you are having an experiment that consists of an interview, and then whenever somebody's asked a question, you want to enter a marker. I can set that up if I go to Setup Data Acquisition, and then I go to my event marking, and then I can say, all right, when I press the F1 key, I'll enter a marker, which will be called a stimulus delivery, and it will be on the EDA channel. And I can have it fixed like this, or for F2, I can have sequential. This time I'll choose a different kind. Okay, and then the first one will be question 1, and then we'll have question 2, and so forth. Okay, now having done that, I will go ahead and save this and show you what happens. So I'm going to press F1 now, and see here we have a marker, And over here, there is the text. And now F2, question 1. And then a bit later on, we have question 2. So that's one way of marking events in our experiments. Another way is taking advantage of the native stimulus presentation capability of the AcqKnowledge software. So let's open up a stimulus presentation file here. We'll come back to software. Okay. Let's open up stimulus presentation. So here we have an experiment where we've added a number of images, texts, and videos. In fact, you can see here I can add all sorts of stimuli, and they're arranged in a sequence so that let's have a look at some of these. So there's some pictures. We have a fixation cross, etc. Right here. And then we can define the sequence of events. And then we can even combine this with eye tracking. So in order for that to work, I must set up my recording. So I'll just do that right now. Let's auto configure. Okay. And enable the eye tracking. And now we see here we have an ARI editor where we've already defined some areas of interest. Now what will happen is if we execute this experiment, markers will appear whenever a new stimulus is presented and whenever the participant actually looks at an area of interest. So how does it work? Let me show you. I'll just skip forwards a little bit. Okay, so we have an eye tracker. We have a screen where the participant sees the stimulus. And then we have the technician's view. So let's go forwards. Now, when a new image is presented, we can see over here in the bottom right, markers appearing. And also, when the participant, like right here, is staying in this, is entering an area of interest, we also get markers. So there's a lot of information right now. You probably can't make out the individual markers, but the point is that the important stimulation events are getting marked automatically by AcqKnowledge itself, which is presenting the stimuli, recording the electrodermal activity, and on top of that, combining this with eye tracking data. So that's another way in which you can take care of markers. Okay, then another way is dealing with markers in virtual reality. Okay, so I'll go ahead and fire up here an experiment in virtual reality. Actually, let me just do the video because this will take a bit long and we're a bit short of time. So I'm going to show you here what happens in this experiment. So the participant is wearing a head-mounted display. And then on the screen here, we can see what the participant's view is. We're recording electrodermal activity right here on the right side. And then from our virtual reality system, we're sending markers when certain things happen. So for instance, I don't know if you can see this, but there's a little green dot right here, which indicates that the user is looking at the middle lower shelf in the store, okay? Right here, middle lower shelf in the store. At the same time, a marker is being sent to AcqKnowledge, like right here, indicating that, yeah, they looked at the middle lower shelf, and that's the marker right here. So this is sort of a complete solution that we have if you're doing experiments in virtual reality. The markers just find their way into the software so you know when events happened. And these markers can include events when somebody grabbed something, when stimulus was presented, when they looked at something, etc. A more traditional way for markers is to receive them via TTL lines from stimulus presentation software such as ePrime, SuperLab, Presentation, etc. In fact, in SuperLab, the latest version supports also markers over the network, which simplifies things quite a bit. But if you want to be traditional and use TTL lines, it's done via the STP100C and STP100D module, depending on which unit you have, MP150, 160, MP200. And also if you have the MP36R, there is actually an isolated port here. So we can make a connection with the stimulus presentation computer, and then we have access to 8 digital lines that can be used as a way to encode markers. So that's as far as preparing the software, getting things ready for your experiment. Now, let's look at data preparation, meaning that we've already collected some data. How are we going to get started with analyzing it? Well, there's some things that have to be performed first, and that's data preparation. Before we do any of that, let's have a quick view of some of the terminology and expected values for skin conductance data, because without that, you don't know what you're looking for. So first of all, the skin conductance level has a certain range, physiological range that we expect between 2 and 20 microsiemens. So if we are beyond that range, we know something's not right. And we also expect certain amplitudes of skin conductance responses, characteristics for latency and rise time. I'm not going to go through this entire table right now. This is from the Handbook of Psychophysiology. And I highly recommend that you all get the handbook and read the EDA chapter. So, because you need to have that background knowledge to help you, first of all, identify artifacts. And let's see what good data looks like and what are some examples of bad data. So here we have good data. A skin conductance response typically climbs fairly quickly. It takes between 1 and 2-3 seconds to climb, and then it starts decaying. Sometimes another one comes right afterwards, but that's the general shape. So this looks nice. And then if we zoom out, this is what a nice, good skin conductance data file would look like. But sometimes you get these, and look at this horizontal scale here. We're looking at minutes worth of data, 6 or 7 minutes, and it looks maybe there are a couple of responses, and the range is very low. We're actually below 2 microsiemens or 2 micromoles. It's the same unit. So that's typical non-responder data. It's just very flat, very low. Here is another example. This is even lower, okay? But it's not that the electrodes were not connected at all to the person. We don't really have any sort of spikes from noise. It's just flat and very low. And nothing you can do about that. I mean, that's just going to be excluded from the analysis as a non-responder. Okay, now, this is something that you will see when your gel is not enough or simply the contact is not very good. These movement artifacts that look like sharp spikes in the data, they are caused by momentary disruptions in the interface between the skin and the electrodes. I have here on myself electrodes in 2 different positions, by the way. So if you do something like that or tug on the leads, that's why Fraser recommended taping the leads, you get these spikes, even if you have done a very good job at signal preparation. So you tape down so that doesn't happen, and make sure that you have enough gel. So you can get these, and these are fairly easy to deal with. I'll show you how to deal with that. And then you have negative skin conductance, which comes up every now and then. Why people asking why they're getting negative skin conductance? Well, first of all, you cannot really get negative skin conductance. This doesn't exist. You cannot have negative skin conductance. What happens is one of four things: either calibration is incorrect, or the recording was not done in DC but in AC mode and the signal dips sometimes, or you set two channels on exactly the same channel number. And sometimes it could be an interaction with bioimpedance measurements, like using the EBI or NICO amplifiers. And that's solved beautifully, by the way, by the new smart amplifiers, because the EDA is isolated and the NICO and bioimpedance are isolated. Anyway, if you have any such issues, it's fixable if it's because of calibration. The rest, not really. Okay, and then let's have a look at some of the data processing steps that have to take place. Let's open up a file here. Okay, file, open, and we'll grab this file right here. Okay, now this file is recorded at 2 kilohertz, like we recommended. But what will happen is if you're processing data at 2 kilohertz, it's going to be slow, and you want to accelerate processing of the data. So what we can do is go to resample waveform. If you have a single channel, you can do resample graph, but we'll go to resample waveform. And I'll just choose something that's above 50 samples per second, because 50 samples a second is fast enough, but I don't want to go below that. So we'll click OK. Now, if I move my mouse over here to the left, we can see we have a new sample rate. The data are resampled. But now we have a problem. Okay. We have a problem because we have these spikes right here, and we have to get rid of them. These are, again, the sort of artifacts that happen from these momentary disconnections of the electrodes. Now, what we are going to do here is use smoothing, median smoothing, to remove these artifacts. So let me show you here graphically what's going to happen. So here's raw data recorded between DC and 10 hertz. And then this is what happens when you apply on the exact same waveform a median smoothing with 1 second window width. This means you imagine like a window going through the data 1 second wide, and then at every point it replaces the middle with the median. So if you have an outlier, it's just gonna throw it away. So this is what will happen though if you, instead of doing median smoothing, just go ahead and apply a 1 hertz low pass filter. So look at the original data. This is what happens if you apply this smoothing, median smoothing. But this is what happens if you instead apply a 1 hertz low pass. It starts to look a bit like a skin conductance response. So if you don't remove these artifacts ahead of time and just apply filtering to the data, they will end up looking like skin conductance responses, and they will mess up your analysis. So very important to follow the exact sequence of steps. And of course, if you have a lot of artifacts that are even wider than a second or even half a second, this method doesn't work. So hopefully you don't have data that's so badly contaminated. It doesn't really happen often like that. So let's go to transform smoothing, and we'll choose median smoothing, and I will enter 62. And why am I entering 62? Because I have 62 samples of data in 1 second. So this means I will be smoothing with a 1 second window. And that's it. These artifacts are gone. Okay, so the next step is to apply a low pass filter to the data. And the most common in the literature is a 1 hertz filter. You can apply also 2 hertz or higher, and those are usually for exploratory analysis. So I will stick with the 1 Hertz. That's through the transform menu again, digital filters. And we recommend using the FIR instead of the IR. So FIR, low pass, and we choose 1 Hertz, keep everything as default, click OK. And at this point, this particular data set is ready for the next analysis step. Just keep in mind, once again, if you do not resample your data and keep it at very high sample rates, even this calculation would have taken quite a bit of time. So let's go for our next poll, at which point we'll come back for the rest of the analysis.
Okay, here we go. I'm going to go ahead and launch the poll. And here we go. Okay, so do you use a standardized effective stimulus set in your experiments?
Brenda, you're muted.
Thank you. Yeah, I do see a bunch of questions coming in, you guys, and we'll answer some of them during the next segment when Fraser's speaking again. And then any questions that we don't get to during the presentation, we will follow up in an email with you all, and we'll go ahead and send a Q&A document out for reference. Okay, let's go ahead and end the poll. Looks like a bunch of people are not using standardize. I'll go ahead and share those results with you. And you can take a look at, yeah, a lot of people using IAPS. Okay, well, great. Thanks so much for sharing, y'all. And we go back to you, right, Alex?
Yep.
Okay.
Thanks, Brenda. All right, so let's go ahead and analyze the file that we started working on. But before we do that, just to make sure we're on the same page as far as terminology. Okay, so when we're recording electrodermal activity, the raw signal, the one that we were looking at so far, is called tonic electrodermal activity, or skin conductance level. So tonic electrodermal activity. And then right within that, if we zoom in here, we see the actual skin conductance responses. However, to identify the skin conductance responses, there are some steps that have to be taken. So you begin with the raw data, the tonic EDA, also called the skin conductance level, or the raw data. And you have to remove the baseline. Okay, and we offer 2 different ways in our software to do that. One of them is simply applying a high-pass filter, which removes the baseline. And another way is called smoothing baseline removal, which means we make a new waveform, which is just this green one, which is just the smoothed original. Okay, so it's smoothed over, subtract it, so subtract the green from the blue, and you end up with the black one on the top, on the bottom, which is the phasic EDA. Okay, so the goal is to start from the tonic signal to get to the phasic signal, because the phasic signal shows the changes in skin conductance, and they're centered around 0, basically. So this is the process, and there are additional ways in which you can derive your phasic EDA from the raw data, but we provide 2 ways to do that. Once you have that, you can pass a threshold. That's what this red line is right here, through the phasic EDA. And whenever you cross the threshold and then you get to a peak, that's going to be a skin conductance response. So you can then know when the responses begin and when they've decayed. So that's basically all it is. Okay, this is another view of tonic EDA and phasic EDA. On the bottom, we have the tonic signal, And when we perform analysis in the software, we place the markers and everything on the tonic signal. Okay, and on the top we have the phasic signal. All right, so now let's say you have a stimulus event right here, and then we have placed the onset of the skin conductance response right here. Notice that is not exactly what visually looks like the onset on the skin conductance level data. That's because if you visually trace the mouse here, that's because we're looking for the crossing, the threshold crossing. So that will usually be a little bit off from what you may intuitively think is the threshold, okay? But that's just the algorithm. So there needs to be a change, a certain change of at least 0.02 or 0.05 microsiemens. And then we're saying, all right, now we have a response, skin conductance response. So from the stimulus to that onset, we have the latency, okay? And then we also have the next part, which is the rise time from the onset to the peak. And then we also have the amplitude, but actually my amplitude here should be drawn from the top to the threshold. Sorry, it got moved at the end. So yeah, the amplitude is just from the onset to the top. Okay. So let's go ahead and do that in the software now. So here we have our EDA, and let's first show deriving the Phasic EDA. So we go to analysis, preferences, and I have two different options. I can do smoothing baseline removal, which we explained, and we can do 0.05 hertz high pass filter. It's up to you which one you want to do. You should read, of course, in the literature which one makes more sense. And then we choose a threshold for the skin conductance, and I'll stick with 0.02, which is the default in the software. And then we also have the option to additionally reject skin conductance responses that are above a certain percentage, like 10% of an individual's responses, as a way of normalizing responses for your experiment. So if one person is getting a lot of very big responses, another one is getting just normal responses, and use the same threshold, that may skew things. So you may say, all right, I want to compare these directly, and I will take for every person certain percentage of their max, and it will be the new threshold. Okay, I won't do any of that, and this is described in detail in the manual how it works. So I'll just click OK over here, and I'll execute this operation. So electrodermal activity, and let's derive the phasic from tonic. It's coming from channel number 2. Okay, so we have it now. It's great. And I had another one before that, so I could probably just delete it. But anyway, we'll just stick to that. And now let's do the next step, which is I will come over here and locate skin conductance responses. So my tonic channel is number 2. Phasic is number 3. Now, what happened very, very quickly here is that skin conductance responses were marked. So the blue drops are the responses, and the little open brackets are the onsets. Let's have a look here. So we have onset, response, and this is basically when we cross down from when we cross 0 again on the Phasic channel. So I'm going to hide this Phasic channel, and let's just look at our data set here. Let's pretend for our purposes that from here to here it was one condition, okay? And we could have already had markers that actually delineate this condition. Could have been watching a movie. So, but let's say we're marking this right now, and I will make sure that my focus areas are turned on, and then right-click, create focus area. I'm going to call this one 1. and another focus area here. And this one will be called 2. Okay, so now we have these 2 focus areas, and I want to take measurements in those. So I'll come over here and choose. I'll choose the event count, EDA, skin conductance response. Let's have them anywhere. So I have 12 here, and if I go to the other one, the other focus area, I have 9. Now, if I look at the delta time, I have delta time and I have event count, meaning that I can extract the rate. I can see how many events I have per unit time, and I can do this calculation very easily if I export the data. So if I open up the journal, I can say, let's go ahead and paste measurements. So I can paste these measurements here, and then I can come up to the second one, and I can do the same thing, paste measurements. So that's just one thing that we can do when we're looking at conditions. Now, let's look at event-related EDA analysis. So if we want to do event-related EDA analysis, we come here. And the difference is when we're doing event-related EDA analysis, so let's make sure everything's the same. Channel 3, Tonic, Phasic, everything's the same as we had it set up before, is that we have now the ability to mark specific skin conductance responses. So that means when you have a skin conductance response between 1 and 4 seconds, beginning between 1 and 4 seconds after a stimulus. So you can have some responses all the time, but when I present an image, for instance, an image of a cat, and I get a response right afterwards, I know it's specific to the cat. Okay, so let's concentrate on that. These are some other reporting settings which we don't need to worry about right now, because we are going to get this report coming out. So let's just click OK. So I'm going to come back here. So you see now how we got special markings, 1, 1, 2, which correspond to, for instance, right here, we have a stimulus presented that has a label 1. Okay, well, right after that, we zoom in here. So the stimulus presented here, and then within the 1 to 4 second window, we have the onset and then the response. So these are now marked as different kinds of responses. These are called specific, and the blue ones are now non-specific skin conductance responses. And we get a table that shows us for the various stimuli what sort of responses we got, what were the amplitudes, what were the rise times, which stimuli did not get a response. So this is the unmatched table. And then we also get information for the 2 kinds of stimuli in this study. There's only 2 kinds, 1 and 2. What was the amplitude, the magnitude, how many got a response, how many did not, where the difference is that the amplitude is the average value of these 6 times when we got a response, and the magnitude is the average for the 6 and the 4 times we did not get a response. So that's obviously a lower number. And these are just following recommendations in the Handbook of Psychophysiology. So all of that happens via the automated analysis in AcqKnowledge. And at this point, I will just go to the next poll, and Fraser will finish up with some last sections on analysis.
Okay, here we go. I'm going to launch the poll, adding another measure of SNS activation using Trev. Okay, so I'm getting a lot of questions. We're not going to have time to get to all those questions, but I did want to let everyone know that we do have a lot of webinars, over 100 webinars on our website, and those are great resources for you. We also have a knowledge base. We have application notes with step-by-step instructions, tons of videos explaining how to do some of these things that you're asking about. And also the support team is available to answer your questions. And we'll have someone reach out to you all at the end of the webinar over the next, few days or something. I have to get all the information organized, but I'm just letting you know that that we will help you out. Absolutely. So I'm going to go ahead and end the poll, and I'm going to go ahead and share the results real quick. All right, you guys are going to have to learn about Trev, it sounds like. Go ahead and close this poll, and now we're going to head over to Fraser's screen.
Let me just show something real quick. You can see here the spots from where the gel was on my hands when I just removed the electrodes, right? So that's how we know you put enough gel. Everything's looking nice and wet still. Okay.
Thank you, Alex. All right, Fraser, I just made you presenter.
Okay, thanks, Brenda. Well, great presentation, Alex, and you queued me up beautifully, because one point I forgot to mention earlier when I was talking about applying gel to the electrodes and making sure you let the electrodes sit for 5 minutes. The reason for letting the electrodes sit for a few minutes before you actually start to record data, that helps to make sure that the gel is penetrating the skin, and then you reduce the impedance levels between the electrode and the skin surface, and then you get cleaner signals. If you just put the electrode on right away with the gel and you start recording, you'll still sometimes get a little bit of noise. So this way, letting that gel penetrate for a few minutes really helps. So my recommendation is, when the participant first comes into the lab and you're setting everything up, the first thing to do is get the hands washed, or even before you're ready to start working with them, make sure their hands have been rinsed under the tap, dried thoroughly. Then apply all your biopotential electrodes, whether that be EDA, facial, EMG, ECG, and then by the time you've completed everything and you're ready to start recording data, the 5 minutes has naturally passed. You don't actually have to hold the participant back and delay the start. So anyway, that sort of addresses one of the questions that I realized I skimped on. What I want to do now is pick up from where Alex left off. Alex showed you how AcqKnowledge does this amazing job of analyzing the data and marking the skin conductance responses, giving you the difference between a specific skin conductance response and a non-specific skin conductance response. Does all of that very nicely. Now, as you became aware while you were watching that, there's actually quite a few steps in that process. You start with making sure that the signals are clean, you remove any artifact that may be in there, then you start to run the automated analysis routines. Well, workflow, which is what I'm going to talk about now, really enables you to standardize and automate that process. Workflow, it's a licensed feature within AcqKnowledge. If you have a license to workflow, you automatically get a license to scripting, and vice versa. The advantage of workflow, there is no programming required in order to automate a lot of these tasks. So if you open up the workflow menu, the top option is the workflow editor.
Hey, Fraser, can you maximize your AcqKnowledge screen so we can see it a little bit better?
Yeah, I'm not really showing that much at the moment.
Okay, right. Yeah.
So here we've got a graphical user interface that allows you to create a workflow. And the workflow will basically mimic the steps that Alex demonstrated in order to prepare the data to the point of analyzing it and then running through the analysis. On the left-hand side, we have all the actions that are available within the software. The actions are the transformations, the filters, and then you get to the analyses, things like electrodermal activity, etc., etc. In order to work through this, you kind of have to have a little bit of an understanding of how AcqKnowledge works. But once you know the AcqKnowledge menu structure and you think sort of logically about the steps that you're going to take in AcqKnowledge, life becomes a whole lot easier. So what I'm going to do is I'm going to ask the system to get the top graph only. That means it's going to look at whatever graph window I've got open, and that's the graph that it's going to apply any task that I want. We can ask it to change the active channel. So if I come over here, say change active channel, and I can say, okay, I want to change the active channel to anything containing EDA. And then I want to duplicate the active channel. So now I've got two identical channels. I can rename the active channel. So I could call this one filtered EDA. And then if you remember, Alex wanted to resample his waveform. So things like before you do any transformation, you usually want to make sure that you are selecting all of the data. So this is going to select all the data in the graph. And we can come over to transformations, and we'll say resample the waveform. And I'm going to use a rate divider of 2. And if I minimize, if I reduce this back down in size, plop this over here. This is data from the ring. It's already clean. I just really want to show you the process of creating one of these and how it works. In the workflow menu, there's a toolbar along the top. This allows me to open a workflow, to save a workflow, and then to run the workflow from top to bottom, or to step through it. So if I decide that I want to step through it, I can click on the first one, and it's found my active waveform. And you can see that because it will mark it with a check and say it's executed that successfully. The next part was to change the active channel. So now EDA, you'll see, is the active channel, and you can tell the active channel on this graph here. It's colors it a creamy yellow on my setup, and then the label is dark gray versus lighter gray here. And I move on to the next one, and it's now duplicated the waveform. So I've got two identical EDA waveforms. Move on to the next one. It's renamed that for me, and it's now selected all of the data, and it will now perform the resampling on that channel. So now we've resampled the data down, and if you recall, these were the first steps that Alex performed. So this gives you an idea of how to create it. If I hit the run button, it will run from top to bottom in a matter of, the blink of an eye. It's extremely fast. So what I'm going to do now is I'm just going to delete these additional channels, remove waveform, and if you notice, the selected waveform is now PPG, and I can remove the selected area, and I'll just say, okay, run this. Boom, it's done literally in the blink of an eye. Okay, so very, very quickly. Now, the advantage of this is this adds to greater standardization within the lab, because every person that runs this workflow, the workflow is going to be performed the same way every single time. Whereas if you have a standard operating procedure and you've got 3 or 4 people all analyzing and preparing data, they all may do things just like subtly differently, but this eliminates that. This will allow you to control that level of standardization. Now again, I'm going to close this out, just discard what we just did, and I'm going to remove this waveform here, remove waveform. So we're now back to the file at the beginning. I'm going to reopen the editor. And I've got a workflow that I created before. This one's more involved, but it follows the precise steps that Alex went through. After the signal was resampled, we then run a median smoothing, and we're doing this at 100 samples, so we're looking at about 1 second. There is no noise in this file. It's probably a bad example if I'm trying to show you how the median smoothing works, but I think Alex already gave a very thorough demonstration of that. Then we will locate the skin conductance responses, and I've set up the Epoch analysis. The Epoch analysis allows us to define a time window, and the software will run through, in this case, 5-minute time periods, measuring the, counting the number of skin conductance response events that occurred within each of the 5-minute blocks. So I'm just going to run this. Let's scale this. So now if we look at this, and I'm going to take Brenda's lead here, maximize this, you'll see that we've got these skin conductance responses, the blue water drops. I don't have any events in here, so I'm not doing event related. This is more spontaneous EDA. Down below, we've got our phasic signal. And if I adjust my horizontal axes, so now we're looking at 5-minute, the main axis mark here is the 5-minute intervals, okay? And what you guys didn't see, but simultaneously, the Epoch analysis went through each of those 5-minute windows and counted up the number of skin conductance responses. Now, if I just come back over to the workflow editor, you can add any number of measurements over here. It doesn't just have to be counting of the events, that's just one I selected. But if you were recording ECG at the same time, you can select the maximum and minimum heart rate over the 5-minute period. All manner of different types of measurements can be automated through the workflow editor. So that kind of gives you a quick show and tell. We do have some really detailed webinars that go into the workflow analysis in much more detail, but I think that's a good sort of way to give you a flavor of what the system can do based upon the demonstration that Alex gave. It kind of layers on quite nicely. So we're sort of running a little bit late. I'm going to hand you back over to Brenda to conclude the webinar.
Okay, well, thank you, Fraser, so much. Really appreciate that. And Alex as well. Thank you for all of your the work that you guys have both done to make this webinar happen. Obviously, it's a really good topic because lots of questions, lots of engaged people. I wanted to show you all a few things before I close. First of all, tons of people were asking about the ring. So if you go to our website and just search for a research ring up here, you'll get to that page. If you scroll down to any page, scroll down to the bottom of any page of our website, you can get your local representative. Wherever you are in the world, your local representative will pop up here. You can simply fill out this form and it'll get an email to them immediately. Lots of people ask questions about other EDA webinars and StimPres and Research Ring. Lots of great webinars here. You can just click on any of these and watch them at your convenience. Here's the EDA section. If you keep scrolling down, you'll get to STEM simulation and StimPres over there. And then finally, you can just go to our support section of our website. We have support and resources actually. And you can, go to our knowledge base, watch video tutorials, find out what else we have available that you're looking for. Lots of great resources. And of course, the guide that Fraser mentioned earlier as well. Okay, so our next webinar is October 22nd. We have a new brain body neurophysiology platform that we're launching. We're in the middle of a launch right now, so we hope to see you there. We'll also be at Neuroscience with all of this equipment. So if you attend Neuroscience, please come by our booth and say hi to Fraser. He'll be there. All right. Let's see. Let me get to my screen here. Also, since a lot of you had so many questions, if you want to have hands-on experience with the equipment, you're more than welcome to reach out to your representative. They can organize, in conjunction with you, they can organize a workshop, and it can be like a full day workshop, and you can customize it to what your research area is. And we've done them all over the world. It's a great way to learn how to use the equipment and really get great experience with it. For more information, okay, so let me just stop here again. The webinar was recorded, and we'll email you a link with the recorded. We did not get to all the questions. I did send some to Alex at the end there, so thanks for answering those on the fly, Alex. We will send a questions and answer document out in the next week or so, as soon as we can get all of the information organized for you. We'll also send a recording of the presentation today. When you close the webinar window, you'll see a survey. We'd love to have your feedback and ideas for future webinars. And then again, I already mentioned this, but you can go to biopac.com for additional resources, guides, screencasts, videos, application notes, and of course, our events. All right, Alex and Fraser, thank you again so much. Really appreciate all the work that you put into this. Is there anything else you'd like to say before we conclude?
No, thank you for attending, everyone.
Thank you.
All right, well, thanks everyone. Have a great rest of your day. Take care. See you at the next webinar. Bye.
Bye.